This is what I want to emphasize. When we started, this is back in 1973. Power electronics was considered as electronics, circuits and devices, static equipment, rotating machines, continuous sample data control. I actually changed this and called it topologies, emphasizing connection of components, magnetics as another component, and control. Nowadays, this subset is controlling the industry. This here, you call it power management, because they put the devices first and everything else is secondary. So they use 50 years old technology and they are not going to change it in another 50 years. And I will just, to explain you the difference, here is one example of what I did recently, which you can appreciate the difference. Just on this, you learn all about a buck converter, right? And this is the buck converter that I mentioned, 48 volt input, 50 volt input, 1 volt output, 100 amps. This switch here sees 100 volts because it has the spikes, so it has to be 100 volt rated, and it sees 100 amps because it circulates the current here. So this switch is rated at 100 volts, 100 amps, or 10 kilowatt, but it delivers 1 volt and 100 amps or 100 watt. How does that make sense? And it's doing that at the frequency because you need to step down with a large 50-to-1 step down. So what's operating? Duty ratio 0.02, 2%, right? But now at 0.02, we can go to 2 megahertz, but 0.20, they have a 10 nanoseconds resolution on a device and so on. But here's a circuit solution. We're adding one more switch, which is this one here, and adding one more component, this famous capacitor, floating capacitor. What happens now? First of all, these two switches operate here at a very low duty ratio, high voltage stresses and so on. Yes, these two are the 50 volt stresses, but they are 50 volt 1 amp and not 100 amps, okay? Or 50 volt 2 amps. And the second, they are in a high side configuration, so-called, so you can use, and this capacitor changes direction of the current, so you can operate with a dead time to have a 0 voltage switching. So eliminate switching losses. Then what about this diode? Yeah, it is now seeing 100 amps on the output, but sees only 2 volts on the output, okay? And better yet, it doesn't have a 100 amp current to turn on and turn off. It starts, this current diode says, in this loop, diode says transistor and diode in series, and when this current goes to 0, this diode doesn't let the current go negative. So I stop here, I'm sorry, can't deliver anymore. Which is great because automatically stops where it should, right? So now you deliver a pulse of the current and this diode doesn't even know, I usually say, doesn't even know that it's switching, right? It turns on at 0 current, and of course when it turns on 0 current, this diode is 0 voltage, right? Or low drop, and turns off at 0 current. So the diode is actually used in the switching, but it doesn't even know that it's switching, because when it starts switching, when it's turned on, doesn't know it's switching, and when it turns off, doesn't know it's switching. You know what I'm saying? Whereas compared to here, which has a 100 volt switch, and you have a 100 amp current, right? Tell me which one is better, and tell me why you should be continuing doing that. And you know what? $10 billion industry is built on this. Worse yet, they repeat that 8 times. Why? They put a multi-buck converter, phase shifted to get a fast transient and so on. Now you can tell me, oh, but Dr. Chuk, you have here a capacitor. Come on. You know, I will make this tapped inductor 10-to-1. And if I have a 100 amp current, one turn on a secondary, 10-to-1, primary side will have a 10 amp. And this capacitor, you can buy a little cheap capacitor, 806 or whatever, which is small and carries 3.3 amp current. You put 3 little chip capacitor in parallel, this is all you need. Okay? And these are 0 voltage switching. The capacitor is very small. The leakage, that's another thing. All transformers and all tapped inductors have a problem because there is one inductance associated with the primary you don't see, but it's always there. so-called leakage inductance, which represents flux which is not coupled between primary and secondary, but it's closed in itself. And that causes a problem that proportional to Li square of this leakage inductor, every cycle as you times the friction frequency, you make losses. So it becomes by definition lossy. Here, this capacitance is part of the circuit and resonates with it when it needs to, and so that is really not any more lossy. So basically this now can operate at 100 kilohertz, be much smaller, have much lower cost, but it has 3 devices, and it has a zero voltage switching, has all of the things here, and yet industry, and of course now they have to use 8 of those in parallel to make a fast transient response. Here, in this one, I can use just a single stage and get a fast, quick transient response, okay? So it's just one example of how the industry is, totally, okay, what happened? Yeah. Here, something then happened again with this UCI mobile net. Is that what it is?
Control.
Oh, control. Oh, okay. All right. So, all right, I'm almost there. So let me just comment on this here without the details. Basically, what I think a topology comparison. What is now is everything is based on a buck, flyback, and continues from there. I'm now working, continue to learn of it because you'll need it. You'll need it to learn later why we need to eliminate it, okay? And what it really is, we need now new system based on a switching method, new switching methods, hybrid storages, and PWM resonant. And then after that, you need to have topologies, and then at the top of that, they make isolated converters, etc. So this here, where is this going to lead to? I will just show you some example here that this is my ultimate goal. Nissan Leaf, this is what it is now. At 100 kilohertz switching, actually this may be a 60 hertz transformer, but 100 kilohertz switching will still result in half of this. You do what? Control and tab?
Just the Windows button.
Oh, I see, the Windows, it just resets. So what is happening is they're talking about these fast charger, but they're half of a car. And they cost $100,000 and they're 300 miles apart. What you need is to have a converter which can do that with a much smaller box, and that's what I'm doing here. So this is what is done now. Straightforward. Bridge rectification, boost converter, and full bridge isolated converter. So many switches, all hard switching, 90% efficiency. So you can't get efficient. What we need to do is get a converter which does everything a single stage. This is 3-stage. We need to do all of these 3 stages in a single stage, which does a unity power factor, draws a sinusoidal current proportional to sinusoidal voltage, has a 1 single isolation transformer, and 4 switches. And that's what I'm doing now. Now, this is one of these, this is my Serbian presentation, but the cartoon from, original cartoon from New York, it says, never ever think outside of the box. Okay, yeah, but here, that's a normal wisdom, but what I say here is, you should really think inside the box. In other words, make it such that now you can make a box inside a converter. Now you can say to me and say, Dr. Chu, but you're talking about improvement factor. Weight 10 times reduced at least, loss from 90% to 99, 10 times reduced, cost 10 times. Are you talking about 1,000 times improvement when we all are talking in electrical power electronics, we are talking about 20% or 30% better than the previous one? You must be crazy. No, I'm not crazy. It just says how bad power electronics at this day is, and how we are dictated by power management companies which sell their devices and they use it in a lousy converter configuration and lousy switching methods and result in that. So, so that's the the bottom line. And I think here is when I talk about single stage, how it can be done. I will post all of this on my in a tab. When you get to teslaco.com, go on a tab download, and you'll find out all of these articles and presentation I had at many conferences, including the Brazilian conference. This is another conference that I did, and so you will see there. You know, this is you see, instead of 14 switches, you have just 3 switches, right? 3 switches, and doing power factor correction, and I put here split it into 2 and got transformer. So I have 3 switches instead of 14 switches, and doing much higher efficiency and all that at the same time. So here is I didn't have a time, and maybe next time I'll show you how you know, we can get you know, the simulation using the state space averaging to basically increase the speed by a factor of 1,000,000 times. So you don't have to wait 5 minutes, you get in a blitz second, and you have no mistakes, no errors, and you have convergence, and you have not to store so much of the intermediate data. But anyway, so here I go to, this is one example of that, and I go to 3-phase. So what is the importance of a 3-phase? Because now you can use for each phase, if you have 3 isolated converters of 99% efficient, you can stack them up and use them output. You can connect them in parallel. And what's the beauty of 3-phase that Tesla invented? Beauty is that the 3-phase currents in the output they will be normally 60 hertz. If you start with a 60 hertz AC, it'll be 60 hertz. It'll be huge capacitor needed to filter out. But all 3-phase currents at 60 hertz exactly cancel. So you don't need any capacitor, not even 100 kilohertz, at 60 hertz, which will be huge. You don't need it, because you use an advantage that the 3-phase doesn't store energy. After all, that's the reason why we can send the power from Niagara Falls to here and don't store energy. And remember how much battery you need to store a little 10 kilowatt or 100 kilowatt in electric car, and you pass some megawatts and create all this light here, okay? Anyway, my concluding slide is this. We don't have a time. First, I always like to put my daughters in it, so that's a given. And they always ask me, you know, Dad, how did you come up with it? And you know, I just my answer to that is elementary, my dear. I started working on this 40 years ago. Okay, and here. This means that this will be even smaller. And who is my ultimate check? My ultimate check, so this is what it's going to be. Rectifier, bidirectional in both directions, but who is my ultimate check? Here it is. I always check with Tesla. I sleep and says, would you approve what I did? And then he kind of says, I think I would do. And I said, okay, shh. Thank you very much. I appreciate it. And in the style of Steve Jobs, I always finish now one more thing. If you like my presentation, tell a friend. If you didn't, keep quiet.
Thank you very much, Professor Chu. About 30 years ago, I listened to Professor Chuk's lecture, and today, you got to listen also. And we're very, very happy Professor Chuk is able to come here and to be with us. And I think you, from his presentation, you already know, he got to be the king of invention. And I want to see all of you become Professor Chuk, become inventors. And I want you to be empowered by this.
Go ahead. I have one last thing. You know, when I was in Brazil, I didn't have a chance. You go up on my download in Finding Media, a lot of pictures. I had a tremendous reception by, I felt like a Hollywood star. Everybody wants to make selfies with me and make 200 photos and so on. But now I found a better way. I have a camera, which is latest and greatest. It focuses quickly, and this camera, when you keep it pressed on this, it sounds like a rapid fire. like you have automatic weapon, and makes in 2 seconds about 25 pictures. So there's no way that one of those pictures won't be, that you'll come out great. So what I advise is that someone comes forward, and I'll sit with the K in front, and if you can scrunch behind so we can get one really selfie of all of us. How's that? Okay?
All right,
So-
that's great.
So I will.
You can help us take a picture, okay? Oh,
Oh, actually, you know what? It's hard because of seat. Why don't you come in front of the seat, and I'll sit with the K in front of all you guys, and you can be right there. Okay? So how is that? Okay, here. So someone. But the problem is, if you make a picture from here, they'll be too close, too wide. So we have to. Actually, we have to move. Someone made to.
Sit over there.
Oh yeah, I'll sit over there, and you make picture from there. Okay, right.
okay, you sit here.
Okay, you just crunch over here as many, so because you have to come close because, and of course he's going to make a professional